Welcome to this chat today with Ros Kerr. I'm Karen Crofts, Director of Hunter Writer Centre, and I'm so delighted to chat with Ros Kerr today all about Nobbys Tooth. So Rosalind Kerr is a geologist who has worked across government and universities and mainly as a community educator too on all things geology. And she's done some wonderful papers and research on Nobbys-Whibayanba headland. And we're going to learn today how it all began and what Nobbys Tooth and Nobbys headland is made of. So I guess, Ros, welcome. We have to start with the story of a number of volcanoes.
We have a photograph here of a volcano erupting, a big cloud of volcanic ash. And if we look at the rocks carefully in detail at Nobbys Head, we can find out that this headland is made mostly of a rock called Toof, which is compacted volcanic ash. And this Nobbys Tooth occurs within the Newcastle coal measures, which occupy the area Newcastle Lake Macquarie. So the Nobbys Tooth is made of volcanic ash. The volcanic ash was originally erupted by a very explosive volcano. Many eruptions occurred over a very short period of time. It was a period of very intense volcanic activity with numerous explosive eruptions. And this occurred about 255 million years ago when a volcano blasted thick clouds of ash into the sky. Now, the volcano lay either to the north in the New England area or possibly to the east on what was then dry land in mountains.
So we're talking a lot of volcanoes, aren't we, that were in the region, and they explosively blew up all this ash. And then what happened?
Well, either to the north or the east, the volcano is located. If it was to the east, it would have been 30 to 40 kilometres away. If it was to the north, it was several hundred kilometres away. We're not quite sure. And the wind blew the ash clouds over the Hunter region. So wind, when you have a volcano erupting explosively, it forms a very big ash cloud that can go very high into the sky. The wind picks it up and can blow it over a very wide area. And eventually, the volcanic ash rains down over the landscape. And in this case of the Nobbys area, the volcanic ash rained down over a wet forest peat swamp, smothering and killing the vegetation. So the trees that were growing in the swamp were trapped and fossilised in their growing position. We can see that underneath the Nobbys Tooth in various locations.
Wow. All right. So here we have one picture of Nobbys Head, Nobbys-Whibayanba. And what are we looking at here, Ros?
Well, this is a cliff section from the sand, the beach, Nobbys Beach, all the way up to the top of the headland. And at the bottom you can see some scree. That's rock that's fallen from the cliff above. So you can't see where the Nobbys coal seam is now because it's under the sand, under the beach.
Oh.
But you can see the Nobbys coal seam, which was originally a forest peat swamp. You can see that seam exposed at very low tide and after the sand's been washed away near the breakwall, not just round the corner from there.
So would that coal seam have been that forest that you referred to that the ash rained down on?
That's right, yep. At this particular location, there are structures in the rocks here that indicate that the volcanic ash, after it had landed on the ground, it was transported to this site by a river. And we can see structures in there that show that it was laid down by a river. But originally, the volcanic ash fell out of the sky, landed on the ground, either in the mountains, but closer by here, and was washed here by a river. So this shows the Nobbys Tooth is made of lots of layers of volcanic ash, and that line there shows the top where the Tooth, the volcano stopped erupting by then, and we started to get some sedimentary rocks from rivers carrying different material, this grounded up bedrock and some thin coal seams.
Yes, so this is where we can say that
a very sharp boundary.
Yes.
The volcanic eruption started suddenly and ended suddenly, and the ash has been, or the Tooth this compacted volcanic ash has been dated at 255 million years old. And those eruptions would have occurred in a very short space of time because there's no other layers in between them. It's just layers of different grain sizes that have been sorted by a river.
Fantastic. So do the straight lines reflect the flow of the river in a sense, or the ash coming in and settling in a layer and then another?
Yes, that's
layer?
right. Yes, so the river would have had a channel, has some channels have been observed in those rocks, and some finer layers, grain layers, have been sort of settled out in more quiet water beside a river channel.
And what's the basalt dike 90 million years ago, just before we leave this slide?
Yes, well, that's an intrusion that's come up from below of molten basalt that's intruded into the rocks long after those Nobbys Tooth rocks were consolidated into hard rock. There's deep down under the ground some cracks, or joints we call them. Cracks through the rocks were formed during a period of uplift of the rock. About 90 million years ago, while the Earth's crust in this area was being uplifted, some cracks started to form from the stress fields from the uplift, and molten rock from deep below, about 100 kilometres below, got squeezed up and cooled in the crack.
Wow, so it's molten rock.
The molten rock has been squeezed up through a northwesterly trending joint or crack, and it's cooled in the cool rock beside it.
Fantastic. All right, we'll move to the next slide. So what do we see here? This is a close-up, isn't it?
A close-up with the danger sign of the falling rocks from Nobbys. Yes, you can see in that photograph that there are a lot of cracks, which are called joints. They're weaknesses in the rock formed by pressures in the Earth's crust. And you can see the horizontal layers, which are the bedding layers in the Nobbys Tooth. The vertical cracks are the joints in the rocks, which are weaknesses, and there's two main directions. There's northwest and southwest trending joints through the cliff, and together with the layers, they form weaknesses in the rock. You can see there's some quite solid looking layers that have rusty coatings. Those rusty coatings are limonite. They're a weathering feature. And quite solid rocks jutting out, and then underneath you can see finer grained or more weak layers, clay layers underneath. This photograph shows the weathering and undercutting of the cliff of Nobbys Headland, and the stronger layers, more solid layers jut out. They're more resistant to weathering, and in between there are weaker layers, which are grey layers, and they're more easily weathered. So what happens is the lighter coloured layers are made of a lot of clay, and they weather very easily. The clay minerals absorb water and start to break down, and the rocks have finer bedding, and the joints are closer together, so they break down more easily. And then the rocks either side are more solid, they're thicker beds, the joints are wider apart, and they get undercut by those softer clayey layers. This is a general picture to show how undercutting causes rock falls. So you can see the more solid sandstone type rocks, which have wider jointing, the cracks, and thicker bedding, are stronger and more resistant to weathering. They break up in large blocks when they're undercut by the shale, which has close base joints and thin bedding. That tends to crumble away. So then the thicker blocks above, stronger blocks, are undercut, and then eventually they're not supported anymore and they tumble down. So that's why we have Nobbys as sort of crumbling away, because we've got soft layers and hard layers.
So what do we see in this one, Ros?
Well, this is an old photograph taken by Edgeworth David, who was a famous geologist back in the 1800s and early 1900s. He became Professor of Geology at Sydney University, and he did a lot of work in the Hunter area, along with staff of the Geological Survey and the university, and he produced a big volume on the geology of the Hunter River coalfields. So that shows the layers of rock, what geologists call the stratigraphy. They name the layers of rock as you can see them there, the very top layer is the Victoria Tunnel coal seam, and most of that was removed to build the lighthouse.
Right, so the Victoria Tunnel coal seam would have been a lot higher.
A little bit higher than that. You can see that on other old photographs, how much used to be there. But at the moment there, you can just, when you look closely at that section, it's mostly just some shale with some plant fragments in it, some little coaly stringers and a little sandstone lens. But there was a little bit of coal above that as well, called the Victoria, and it's called the Victoria Tunnel seam. But below that, all that section there, all those layers are called the Nobbys Tooth, and that's a recognised unit in the Newcastle coal measures, and it can be traced all the way to the Hunter Valley, down the coast into the Hunter Valley.
Yes.
And this is the thickest section here, but this is the most northern outcrop and the thickest outcrop of this rock. And because it's made of tuff, volcanic ash has special properties, and it has geochemistry. The geochemistry of that layer is used to trace it a long way away, 150 kilometres from here.
Wow.
To the
Yes,
west.
I believe it does go to the west, but it also does go down
goes to the south as well, yes. Yeah. You can see it on the coast all the way down to the northern headland of Dudley Beach.
Yes. And then it disappears, I believe, under...
Then it dives down.
Dives down under the sea and continues on towards Sydney.
Goes down to Sydney. The Nobbys coal seam, which was originally a forest peat swamp, was annihilated by the volcanic eruptions, the first volcanic eruption that formed the Nobbys Tooth. We can only see that these days when the sand is washed away from the beach.
Mm.
This is a cross-section of what the peat swamps looked like in those days when the Newcastle coal measures were being formed 255 million years ago up to 252 million years ago. I've modified this slightly from Diesel, who was the professor of geology at Newcastle Uni for many years. And you can see the kinds of plants that made up the peat swamp. The Glossopteris was the most common plant as far as fossils go that you find. There's other kinds of plants as well. And the water level at this stage, when the Nobbys Tooth was erupted, the peat swamp was what's called a wet forest peat swamp, and the water level was quite high. The plants had their roots in the water. So the peat swamps existed over a wide area for a long time and dominated the landscape. So the volcanic eruptions were only a very short period of time. Most of the time the area was covered in peat swamps.
And did I hear you say when we were talking earlier that there was also this is what the landscape looked after the volcanic eruption period, that it went back to looking a little like...
Yeah, eventually it went back to another coal seam. Yeah, so the vegetation was able to take hold again. This is a close-up of the cliff section to look at the layers that make up the Nobbys Tooth. It's not just all the one kind of rock. There's rocks with different grain sizes and different textures. So I've divided the rock types into three main types because it's easier to describe that way. So at the top of that layer, you can see what I call a sandy tuff, where the tuff is made of little grains of feldspar and quartz and some biotite, and the grains or the broken up crystals are sitting in a matrix of clay minerals, which is broken down fine volcanic ash, and also some volcanic glass shards.
Now, you use some words there that maybe some non-geology people might need to know. What's feldspar?
Yeah, well, feldspar, quartz and biotite are minerals that form in rocks deep underground. So before the volcano erupted, some crystals formed in the molten rock, and in this case, there were some quartz crystals, like you see quartz in granite, for example. You also get feldspar in granite and biotite. So these crystals cooled or formed in the molten rock before it was erupted. So when the molten rock was erupted by the explosive volcano, it carried up crystals within the molten rock and exploded out the top of the volcano, and some of the crystals get broken by the explosions, and then the rest of the molten rock, some of it forms pumice, which is super chilled, very volcanic froth with lots of gas bubbles, and some of these pumice fragments are very, very tiny and have little gas bubbles in them, and they get the gas keeps exploding out of them, and they form little glass shards. In other words, little fragments of volcanic glass, which makes up a lot of the volcanic ash. And then after it settles on the ground, it can be converted into clay minerals.
Right, yeah. So these are just, what we're looking at here is different types of Toof that has different composite of minerals.
Little different composition of minerals.
So tell us about silicified.
Silicified Toof is a very hard type of Toof, very extremely fine grained and hard, and often doesn't have any layers in it. And it was formed by the alteration of some of the volcanic ash that settled on the ground and compacted. Some of it might have had little grains in it, little crystals, and lots of glass shards. But after burial, it's been altered where the silica, which is one of the main components of the rock, has been redistributed by weathering and maybe during burial, redistributed to make the rock extremely hard and fine-grained. So we can't see the original texture in the rock, but it's just a very hard, silicified rock. And in the early days, it was called a chert because it was very hard, and chert is a sort of just a silicious, very hard silicious rock.
I've heard of chert mentioned by First Nations people. So this is all leading up to what we're going to head to, aren't we, about the importance of that silicified Toof. So the point about all this, though, is what I've learnt is that all this is formed from volcanic ash. It's not from lava, which is different.
Yeah,
so lava is the melted rock coming down the mountainside, the volcano side. But this is all formed by volcanic ash coming through the air, then settling, blown by the wind, brought by the river, settling, and then, so that's what's so fascinating about this headland, is that it is all volcanic ash, and this is the different types of mineral composites make up sandy Toof, silicified Toof, and shaly Toof.
The shaly Toof, well, some of the volcanic ash was very fine-grained and was sorted by the rivers into layers of finer-grained material, and because it contains a lot of volcanic ash, which very fine volcanic ash, it's been weathered to clay minerals, and they break down really rapidly, and so the layers there are quite crumbly.
Yes.
So you can see that they're quite crumbly grey layers. Now they're just going back to the other two Toofs. They tend to be a grey or creamy colour, mostly light grey colour, and the jointing in those ones is much wider apart.
And the rusty colour is the limonite?
The limonite occurs after the rocks have been formed, and rainwater carrying dissolved carbon dioxide is slightly acidic, and that'll percolate through the rocks and pick up iron from the minerals, such as biotite, contains iron, and will deposit this iron in solution in cracks when it's exposed to the air.
Right.
So it comes out of solution, the iron comes out of solution when it's exposed to the air, when air gets into the cracks in the rocks.
So it's like rusty rocks.
Yeah, so they're rusty, they're rusty coatings. So this is an example of the sandy Toof, which you can see there's got little grains in it, and they're actually feldspar crystals, little white angular pieces of crystal that have now been replaced by white clay. So they look like white specks. And there's a little coaly fragment there, like would have been a little bit of wood, got trapped, carried down by the river. And most of the rock there is just a matrix of clay minerals. The clay minerals, mostly kaolinite and montmorillonite. So they're caused by the breakdown of volcanic ash.
So the feldspar crystals were what originally came with the ash, as the ash settled down, and then what's the word replacing mean? So do they actually move into becoming white clay, the feldspar crystals, or do they get literally replaced by other sediments?
Well, the feldspar crystals were the crystals that cooled underground and erupted as part of the volcanic ash. And then when it settles on the ground, water seeps through the pile of sediment, and you get chemical breakdown of the feldspar to white clay.
Yes, great.
You add water.
Yes, fine, fantastic. Yeah. It's really quite pretty,
There's
isn't
also there's quartz crystals there, but they're hard to see in that picture.
Right. Okay.
This is a lump of sandy tuff that has fallen from the cliff. You can see the size of it in centimetres. See the texture there? It's got a sort of a grainy texture. And then there's one underneath. That's another photo showing some little white specks of white clay, which are replacing feldspar, and a little bit of black biotite there.
Oh, we've got a little bit of biotite.
A shiny black mica that you find in the Nobbys Tooth. You see the overall texture of that, which looks different to what we're going to see next.
And biotite was the one that you said has iron in it.
Iron, that's right, contains iron. So this is a block fallen from the cliff of the sandy tuff again. You can see that the jointing has limonite on the faces, and they're almost at right angles, and that size of that block, I'll have to measure that one. It's got some, on the bedding plane, that's just the top layer, you can see some little black blobs, and actually remains of plants, the carbonaceous remains of plants that were washed in with the crystals and the volcanic ash. Some little fossil twigs in the sandstone as well, little specks of plant material there. Now that's a close-up of a fallen block showing layers or bedding. They're defined by different grain sizes. So some layers have bigger grain size than others. So the bedding is defined by variations in grain size, where the river has sorted out the grains into different sizes. There's the currents of river. We can see 3 different sedimentary structures there, which are formed by river flow. We've got some horizontal bedding at the top, where the river has, that's obviously the top, that came last in the sequence of that little picture. And beneath we have some cross bedding, which is a slanty bedding. That's formed by a river current forming little sand dunes in the bed of the river. As the river flows downstream, you get some ripples, or quite big ripples, and a cross-section of that will show that cross bedding, and that points the way the river was flowing. So it's flowing, in this case, to the right. It's a cross-section of an underwater sand dune. And then the scour and fill is where the river has eroded the top of a previous sandy layer and then filled it up with more sandy material. When I say sand, it's actually volcanic ash of sandy-sized material.
So is it possible to work out the timeline roughly between these beds, in that the sloping cross bedding, that's obviously come before the horizontal bedding? How long does it take for that cross bedding perhaps to settle and, in a sense, solidify, would we say? Or does all the solidifying happen a lot later of all the beds?
Well, there's a little bit of erosion between the layers, because you can see the scour and fill. This layer's been deposited before the next layer. So a little bit of erosion, but it's all fairly quick because there's no major breaks there. There's no much change in the rock type there.
No, in the rock type.
So it's all fairly quickly.
So what are we talking? A few hundred years between?
Oh, no, maybe a few hours or
really?
a day or so, not much.
Right.
Fairly quick in that case.
Now we get to the exciting.
Now this is a different kind of rock type, which occurs in the Nobbys Tooth pile, that big pile of rock. And it looks different to the other ones because it's quite, it's very fine grained, extremely fine grained. It has very smooth texture and sort of grey to, can be sort of a bit darker grey than some of the other rocks. Then the sandy type of tuff is usually light grey or can be creamy coloured. This is a bit dark, usually a bit darker in colour. And sometimes it has faint layering. There you can see some faint horizontal laminae, or they're fine beds. But because it's fairly massive, which means it doesn't have any cracks, much jointing in it, or horizontal layers, it's very compact and massive, so it tends to break with what's called a conchoidal fracture, or subconchoidal fracture if it's not so well developed. But there you can see the curved surfaces. It's like breaking glass, and you'll often see little ridges within those curves, like the growth lines of a shell. Conchoidal comes from a word meaning shell, so curved like a shell.
And we can see a small one here where the hand is, but there's also a bigger one here.
There's a big curved surface there. So it makes curved surfaces when it breaks. That's just fallen off the cliff like that, and it's broken that way. And that could be suitable for making Aboriginal tools because it'll break with curved surfaces, which can be used for shaping tools, and also very sharp edges and points. Now, the photograph below is a better piece, another lump of silicified tooth fallen from Nobbys Head. It doesn't have any layers. It's just got a joint face, which has some rusty coating of limonite on it, but it breaks with quite a good conchoidal fracture, which means that when you hit it with another rock, you can shape it into rounded edges of tools, into sharp blades or points with those curved surfaces, and it's very hard. There's just a couple more examples of the silicified tooth, which could be used to make Aboriginal tools with the nice fine-grained, very fine-grained, and the sharp edges and the curved fractures. And that's sort of a creamy colour on the outside and grey inside. And there's an extra good piece. You can see the scale by the little sand grains there. Now, Aborigines picked up pieces of Nobbys Tooth not only around the base of this headland, but also below the cliffs at Merewether and Burwood Beach and the Glenrock area, where the Nobbys Tooth occurs higher in the cliff, comes down to sea level at Glenrock, and the rocks are always falling down from the cliffs. Or sometimes more after storms, you seem to get more pieces falling down. Today you can pick up pieces on the rock platform at Merewether, and the Aborigines were very good at sorting out which pieces would make a good tool. A lot of rocks that fall down aren't any good, but they're able to home in on these particular silicified tooth pieces that they knew that if they hit them with another rock, they could shape tools, useful tools for themselves.
Here is an example of one from a site only a few kilometres from Nobbys-Whibayanba headland. And this is a fine example, isn't it, of, is this silicified tooth?
This is a silicified tooth from Nobbys, probably came from Nobbys, or Nobbys Tooth, whether it was from Nobbys Head land or from Merewether. But you can see how the curved fractures make nice curved, you're able to make nice sharp points with it by having the curved fractures and hitting the rock the right way. You had to be very skilled at doing that to get the rock to break as you wanted it. So you get a lot of waste flakes where they start with a big lump and they have to chip lumps, chip bits of it off. And so a lot of pieces fall off that were just, they call waste flakes, because they're aiming at getting a particular shape. And so they chip away till they get the shape they want. And you can get a joint surface forming a flat platform. You can see at the bottom of that, it seems like a joint surface there, a flat platform. And then it breaks internally to form nice curved surfaces with sharp edges and points.
Yeah, fantastic. Great.
So they last in the archaeological record a long time because they're such a solid rock type. Whereas you try to make an Aboriginal tool out of the sandy tooth, it just wouldn't work because it would just break the wrong way. It would just break into slabs and blocks. And as I've got a piece here.
Yes.
It breaks along the layers, whereas these silicified tooth, say, pick pieces that don't have any layers.
Fantastic. Well, thank you so much, Ros. I've learnt so much. I'm so much clearer now on Nobbys-Whibayanba, when it was formed and what it's made off of. So thank you very much.
You're welcome.